Hey programmers, welcome back to day 13 of the Advent of Code. Let's jump right into today's input file. So here's today's file. We're always going to have two lines and we can interpret them in pretty different ways. So for the first number, that's going to represent basically the time that we want to depart, right? So let's say we're going to go on a journey. 9:39 is basically the earliest bus that I want to take. They also tell us in part 1 that the X's represent buses that are not in service. So we'll just look at the number buses. And what's really convenient in this problem is the buses follow a particular schedule. Basically, the bus number is going to correspond to how often the bus appears. So bear in mind that through all of this, we're considering our time units as just in integers, and every unit just represents 1 minute. So if you considered some times in which the very first bus shows up, it appears in multiples of 7, right? So 7, 14, 21, 28, and so on. And this actually occurs for all of the different bus numbers. So based on the bus ID, we know that that bus is going to appear basically on multiples of that bus ID. And when it comes to what we want to do for this problem, they have us solve a very particular question. That is, if I want to depart at 9:39, they want us to figure out what's the earliest bus that we can take, right? So solving this part 1 is pretty straightforward. We just want to ask, is 939 divisible by any of the buses? And it's not, right? It's not divisible by any of my 5 bus IDs. So I can't really leave as early as 939. So I'll just increment that by 1. So now I have a 940. And I ask the same question, is 940 divisible by any of my buses? It's not, so I keep checking, right? Just increasing my time at every iteration. Now I have 941, also not divisible. 942, also not divisible. 43, not quite divisible. But when I finally get to 944, that actually is divisible by some bus. And in this scenario, it's actually bus 59 that works out here. And so in the context of the Advent of Code problem, they want us to return very specific information. They want us to return the amounts of time that we actually had to wait, like on the platform. So my initial waiting time was at 9:39, and the next available bus appears at 9:44. So if I take their difference, just subtract them, that means I waited a total of 5 minutes. And what they want you to do is really take that 5 minutes and then multiply it by the bus ID that appears at that time slot. And so 295 is the final answer we should return to the Advent of Code. So all in all that logic doesn't seem that difficult to implement at all, really just some for loops as well as some conditional logic. And we're definitely going to use the modulo operator, right, to check if a bus is showing up at a particular time. So with that, I think let's jump right in. So here's my input file. Notice that it just has 2 lines. Let's go ahead and start by just reading those lines. We know that the first number here represents the actual earliest time, and then the second line represents the actual bus schedule. So after I get the array of those lines, I know it's only 2 elements, so I'll call it, we'll say line 1 as well as line 2. So that should give me my nice output as lines. And we'll just convert the very first one into a number. It's straightforward enough. So it should be as simple as const, we'll say earliest, equal the number cast of line 1. And then for the other line, I'm going to split on the commas, right? So that'll give me a nice array. So I'll say const, we'll say buses equals, I'll say line 2 dot split. If I just split on the comma, then my buses will also contain the actual x's. So let's see what that looks like. Let me run part 1. Nice. So I do want to ignore the x's. They tell us that, hey, those x's just represent buses that are out of service. So I'll maybe filter those out. So I'll say dot filter. And so for each bus, I want to really make sure that the bus is not equal to an x. Then along with that, I also want to convert these into some numbers. So maybe we'll express it like this. I'll filter out the x's and then map by taking all of the numbers now and actually making them of the number type. Because right now they're just strings, right? So I'll say bus, I'll pass it into the number. So now I should have some nice just arrays of these numbers, right? Ignoring all of the x's. Cool. Now to get this one handled, it's really simple, our algorithm. All it is us starting some loop. I'm going to begin that loop at the earliest time. So I'll say time equals earliest, right? And then what I'm going to do is just keep iterating until I find the first bus that appears. So I can really write like a true here because I know that eventually we'll find some number that divides into mine, right? So what I'll say is time plus equals 1 from here. Cool, and all I want to do is check, are any of my buses appearing at this time, right? I'm already at the earliest time. So I'll check, really a for loop. So this iterates through every element of that bus array, so every number over here. And quite simply, if the time is divisible by the bus, so if I divide it and the remainder is 0, then it's a time that I should actually return, right? So I have the time over here. And don't forget that in the context of the problem, they really want you to take your earliest time and really subtract that from the time right now. So this would give me the time weighted, right? So my earliest I kind of get to the platform is this quantity. And then I have to actually wait a little bit until the first bus appears. So I'll call this my const wait time. Then it's just a matter of, like they say, return the product of the wait time by the bus that just came. So something like this. So I should get the answer 3035 for this. Let's give it a run. It is going to return. Nice, and there we have part 1, a very, very straightforward problem. With that, let's talk about part 2. So for part 2, we'll go over this particular example. Notice that it is distinct from the example on the actual website. It's just a little shorter, so it should be easier to manage. And so we're going to have the same setup as previously. So you can imagine that all of these buses appear at fixed intervals. In particular, a bus is going to always appear at a time slot that is a multiple of that bus ID. And so let's say that we were looking at very particular intervals. And so we're going to start by saying that, all right, let's say our first time is 865. So let me mark off the buses that appear at the 965 time slot. The only one that actually appears would be bus 5. And I can fill out the other time slots in a very similar way. Notice that the time interval just ranges from 865 up to 870. And at this point, we've actually had a very interesting pattern. Notice this kind of diagonal that we formed. And this is really what we're interested in. What this describes is a basically interval or a time starting at 867 where all of the buses appear sequentially, right? Just 1 minute apart. So what we have to recognize is we really want the buses, depending on the order that they're listed within our input file, to appear sequentially, right? So bus 3, then bus 7, then bus 11, then bus 5. Notice that they're all not appearing at the same time. Rather, they kind of come in a staggered order where one bus comes 1 minute later than the previous. And in particular, we should return the first time when this happens. So in this case, I want to return the 867. So I want to return the first time in which all the buses appear in succession 1 minute after each other. So how can we go about solving a problem like this? This definitely feels like one of those problems that there's definitely some, math trick to it. And I think one intuitive one we can use right now is to recognize that all of the bus IDs in anyone's input file always tends to be a prime number, right? That's actually a really big piece of information and can make our implementation much easier. And so what's so special about prime numbers? Well, for all of these numbers that are prime, I know that they share no common factors, which is a really, really big advantage. Let's see what that kind of implicates. If I took some two buses, let's say I took bus 3 and bus 7, if I actually multiply them together, that effectively gives me a bus that almost represents both of them kind of synchronized, right? I would call it bus 21. Now let's kind of see, what I'm saying here, right? Why is it okay to say that bus 21 kind of covers or synchronizes bus 3 and bus 7? So let's take a little look at the chart. So here's some increasing numbers starting at 0. And notice that this pattern actually would occur even as we approached infinity, right? So what I'm going to do is mark off all of the multiples of 3. So they would look something like this. Note that all multiples of 3 in the context of the problem, they're basically the times at which bus number 3 is going to appear. And I'll do something similar for bus 7. So bus 7 appears at all of these times. Notice that when my time is 0, both buses are there, and that makes sense because 0 is going to be a multiple of basically any number. And then after 0, the next time these buses appear together at exactly the same time would be at 21. And I know because we're using modulo here, modulo gives us a very cyclic pattern. So we can say that the period or the cycle length for these two buses is going to be 21. In other words, if you continue this pattern past 21, you would see it appear again and again, right? And so why is that information useful? Well, we can actually abstract this into some other bus IDs as well. So in particular, what we're assuming here is that 21 is the least common multiple of 3 and 7, right? So that's why 21 is special. Using some compact notation, we can say that the LCM of 3, 7 is 21, which you might notice happens to be exactly 3 times 7. And that'd be true for other bus IDs as well. If I took the LCM of 5, 11, it would be 55, which does happen to be 5 times 11. But we should watch out here. This is only true when our two numbers are prime. So in particular, we'll say that the LCM of a comma b equals a times b if a and b are both prime. Because all the bus IDs in our problem input are prime numbers, we'll use that to our advantage. But in general, right, I can show you a counterexample. Let's say you took the LCM of 6 and 4, right? 6 and 4 are not primes. Their LCM is 12, which is not their product, right? 6 times 4 would give me 24. So do bear in mind that this is only safe to say when your numbers are prime. What's great about this is we can actually extend it. So if the least common multiple of a and b is just a times b, of course, meaning that a and b are also prime, then we can also say that if I wanted the LCM of a, b, c, then I just multiply all of those together if they're prime. And likewise for any arbitrary number, right? The LCM of a, b, c, d would just be their grand product. And so we're going to use that to our advantage when we actually solve this one. So what's an algorithm or a well-ordered process we can use to kind of reason out what the bus time is to have all of these buses appear one after the other, right? It could potentially be a very large number. So here I have my inputs along the top, and what I'll also do is label them in terms of their indices that they would appear within my input array, basically. And the reason it's going to be important to also denote their index is that I know I have to stagger these buses, right? They have to appear one after the other. In other words, I can say that bus 7 should appear basically 1 minute after bus 3, and then bus 11 should appear 2 minutes after bus 3. So it's kind of somewhat of an offset, right? And so let's say that we're consuming our very first bus. We know we want to take this bus first. So we're going to start some counters. We'll set our time equal to 0, and our step size is just going to be based off of our current bus, right? So you can imagine that if I took the bus around in a circle, it would just take exactly, 3 minutes of time. So now that I've actually incorporated my very first bus into my initial variables, my initial state, I actually can consume the second bus now. Right. So at this point, what I do is kind of figure out when the next departure should be. So if right now my time is 0 and I have to take a bus 1 minute later, right? It's almost as if you're waiting on the platform for 1 minute. Then what I can do is figure out my next departure. So I take my current time of 0 and I add 1 because that's the offset or the index of bus 7. And that means I have a result that's equal to 1. And now I ask, right, is a bus number 7 going to appear right now at time 1? So is 1 divisible by 7? That's not the case. And so I keep checking some other numbers. What I do at this point is actually increase my time by the step size, right? So notice that my time was 0, but now it's 3 because I added the step size into it, right? The step size comes from the bus I just took, right, which is bus 3. So that means that my next departure is my current time of 3 plus 1. Again, accounting for the minute I have to wait on the platform, which gives me 4. Is 4 divisible by 7? That's not the case, so I kind of continue in this fashion, right? Now I have my next departure time at 7, and I ask, is 7 divisible by 7? And that's actually true. So this would be a scenario where I'm kind of taking a bus 7 right now. So a few important things happen here. What I should do is multiply into my step size my current bus. So not only have I taken bus number 3, but I've also taken bus number 7. So I multiply 7 into that thing, right? 3 times 7 gives me 21, right? Similar to what we did with those prime numbers earlier. And now I can actually consider my next bus in a separate iteration, right? I'm at bus 11. My current time is 6, so I kind of do the same logic. Notice that now I do 6 plus 2 because bus 11 has an offset of 2, right? So that gives me 8, and I check, is 8 divisible by my current bus, or is 8 divisible by 11? That's not the case. And we're going to continue many iterations very similar to this. So notice that I'm increasing my time by 21 every time. And eventually, I'll find something that is divisible by 11, right? So when my time is 174, once I add the offset of 2 into it, that gives me 176, and that is indeed divisible by 11, right? So that means I'm ready to proceed to using my next bus, but I should also be sure to multiply my step size by that bus I just took, which was the 11, right? So 21 times 11 gives me my new step size of 231. Now I'm trying to use bus 5, and its offset is 3, right? So my current time is 174. Add a 3, that means 177. And I check, is that divisible by bus 5? It's not the case. So I keep going a little bit until eventually I have at time 867 something that is divisible by 5, right? Notice that I do have to add the offset of 3 into the 867. It gives me 870, and that works out perfectly. And at this point, I finish taking every bus, or I'm done iterating through all of my buses at the top, and my final time is 867. And that's the actual answer that I should return to the advents of code. So the algorithm here is definitely pretty creative in using the prime numbers, and it's really, really short to implement. So let's jump right in. So here I am in my part 2 file. This is basically all of the code we wrote for part 1. As we work through this one, I'll go ahead and use an input file that's identical to the one that we actually just sketched out. So I'm going to pass in my example file right now. Cool. So there are a few things we want to watch out for over here. So when it comes to actually like parsing our initial information out of our input file, we don't need line 1, so we can ignore that part. And when we split all the buses out of line 2, we actually don't want to just ignore the x's, but technically x's represent buses that appear like every minute, no matter what. So maybe I'll have a nice map for those. So what I'll do is maybe check some ternary here. So I'll check if the bus is equal to an x. I do believe it's a lowercase x, right? So input file, yeah, it's a lowercase x. So our bus is an x, and treat it like the number 1. Otherwise, it's already a number, so they just convert it into a number. So that should be some nice parsing of my input. And then from there, what I want to do is now actually begin my main algorithm. So in the context of the drawing, we started out by really creating, it looks like 2 main variables. We're going to have our overall time. So I'll say let time starts at 0. Then I'm also going to begin my step size. So I'll call it step size. I'm going to initialize the step size variable just to be the very first bus. So bus is at index 0. And then from there, my overall logic is to iterate and basically use up every bus. Since I already incorporated the bus at index 0, I'm going to start this bus index at 1, right? And I'll go while I is less than buses.length, very classic code. And of course, an I++, right? Nice. Let me also grab the current number that corresponds to the bus. In other words, the bus ID. Say bus equals buses at index I. Nice. And now I have my tricky logic. So what I have to do is figure out basically the next time that is in sync with the current bus I'm trying to take, right? Taking into account my offset. So the move here is I need some while loop, right? And then in this while loop, what I want to check is my current time plus the offset. So why do I have to do the plus I over here? Remember that we have to wait, for the next minute to come around before we can take that bus, right? So I'm going to account for that over here. So I'll say time plus I and check if that quantity is divisible by my bus, right? So I'm going to basically iterate in this while loop while it's not divisible. So that'll give me this body to write inside. So what I want to do if I'm looking for something is also increase the time. So I'm going to keep incrementing my time by the step size. So this is going to implement the kind of algorithm we described on the whiteboard. So notice that once I actually increase this quantity to a time that is divisible by the bus, then I exit this while loop, right? So this while loop will only keep increasing the time until the bus actually divides into this number. Cool. Notice that my time plus I is only for the sake of the comparison, although I'm not actually adding I into the time. And this is important to do because in the context of the problem, what they want us to do is return the time of the first bus that this kind of diagonal pattern happens. So this is looking pretty good. Once I finish this while loop, that means that I'm done with this bus, so I need to incorporate it into my step size. So I can just do step size times equals that bus. And this should be pretty good. So what effect does this have? Well, I want to make sure that I don't like lose alignment for any of the previous buses that I used up. If I just multiply this bus ID into my step size, then remember now I'm just kind of hopping around in a full circle, and that won't cause any misalignment for the previous buses that I iterated through. So with that, that means after our for loop is done running, it should be as simple as us just returning what the time is, what the final time is. And that should be the time that represents when we should take the very first bus. So if this is working, we should get that 867, I believe, just like we traced through, because I have this particular test input. So let's give that a go. We'll run node part 2. Nice, I get 867. Now I'll run it on my large input file, which is some very huge number for my particular input. Look how big it is. It starts with a 7 and it's very large, so we'll just go ahead and run this. Notice that it doesn't take quite a long time to execute though, because we're taking some very big, step sizes here if we're multiplying every bus into it. Cool, so I think that wraps up part 2 of day 13. I do think this was a pretty tricky problem. It does help if you're kind of familiar with some number theory and some math, but hopefully, now that we've explained it, the mechanics are pretty straightforward and the implementation is definitely the easy part, right? Coming up with the idea is probably the hard part for this problem. So with that, I'll catch you tomorrow for day 14.